there were just a couple of things that I thought we needed to follow up on after class this afternoon. This is Wednesday, November 4th. The first thing was actually the warm-up question. Normally, I put warm-up questions on mostly to make sure that you guys have a chance to check into Learning Catalytics, make sure all the technology is working, and most of the time the questions are fairly straightforward and everybody gets them. I was surprised to see these results today, and we didn't really have a chance to go over them. I had hoped at the end of class to have time to come and do it again, put this same question on again, because it may be that it would have come out differently. And mostly I think the problem had to do with reading the question carefully. So let's look at what the question says. It says the red triangles in our solution represent anions. So that means the red triangles are negatively charged. And the yellow triangles, and the yellow circles, are cations. And what we can see is we have 2 times as many cations as we do have anions. And so that means the solution here is going to be A, because only sodium sulfate is a formula that has twice as many sodium ions, cations, as sulfate ions. Interestingly, to me, choice D is what you would get if you read this backwards and said, oh, I've got the red triangles are cations and the yellow circles are anions, then I would need twice as many anions as cations, and that's what I have in D. What's interesting to me is you also have that same scenario in E, where you have twice as many anions as cations. But a lot fewer people chose E than D. So take a look at that again, make sure you understand what it is, and post questions on Piazza if it doesn't make sense. The second thing that needed a little bit of follow-up is this last model, which focuses on acid-base reactions. We got through a good piece of it, and I've just recapped here the answer to number 1, which is the equation of the strong acid HCl with the strong base NaOH. Number 2, which is the reaction of a strong acid, sulfuric acid, with a strong base, lithium hydroxide. And in red, I have underlined the spectator ions. We talked about in class what the net ionic equation is, but I just wrote it up, and I'd like to take a minute and do it kind of longhand so you can see where the net ionic equation comes from. What I'm first going to, and I'm going to do it for number 1 first. What I'm first going to do is I'm going to create the full ionic equation. So remember that the ionic equation is where we write it all out in terms of its ions. So here's what it looks like. Because the HCl is actually dissociated H+ and chloride ions, we write them separately. Because the sodium and the hydroxide ions are actually dissociated from one another, we write them separately. And in the products, the sodium and the chloride are dissociated from one another. And from here, we can see if we underline all the spectator ions, what's left is H+ plus OH- goes to water. And so this is the net ionic equation. We could do the same thing for number 2. We will find it has the same net ionic equation. If we look at number 5, what compound is frequently the product of an acid-base neutralization reaction, the answer to that is water. That's the real chemical change that that has occurred. We've produced water. And of course, water is a new substance that instead of being combined with ionic bonds, like everything was in the reactants here, we now have a new substance that's held together by covalent bonds. In both of the reactions, which were acid-base neutralization reactions, a second compound was formed. In the first case it was sodium chloride, in the second case it was lithium sulfate. So the second product of an acid-base neutralization reaction, in other words, the second thing with it we would draw in this kind of reaction, is the ionic compound, often called a salt, that is the combination of whatever the spectator ions are. This allows us, in number 7, to look at an interesting pattern. In the ionic compound that's formed, meaning the sodium chloride and the lithium sulfate, which reactant does the cation come from? In other words, here's our cation. Where did it come from? It came from the base. Same thing here. So the cation comes from the base. Which reactant does the anion come from? Well, we can see the anion chloride came from the acid. The anion sulfate came from the acid. So the anion must come from the acid. The last question we want to consider is question 8. It's actually on the next page, but I'm just going to put it here in this blank spot. The question asks us to write a balanced molecular equation for the reaction between aqueous nitric acid and lithium hydroxide. So let's write down the formulas for those two reactants. So we can look at these and do one of two things. We can recognize that it's an acid-base reaction, and so the products are going to be a salt and water. The other thing we can do is just say, you know what, these are two compounds made up of ions, and I'm going to think about a double displacement reaction. In other words, I'm going to think about an H plus coming from the nitric acid and an OH minus coming from the lithium hydroxide. And when I do that, the product that I would get is water, which is the combination of H plus and OH minus. That's a liquid, and again, it's not aqueous, it's a liquid because what we've produced is this covalently bound molecule. The other product is going to be the salt that's formed from nitrate ions and lithium ions. That happens to be lithium nitrate. Lithium is a +1 ion, nitrate is a -1 ion, so when I put them together, they come together in a 1-to-1 ratio. But if one of them had a different charge, we would put them together in whatever ratio was needed to have a neutral compound. Now that we've predicted the products, we can double check that the equation is balanced, and it is. I've got one more piece of information to add to this particular activity, and that is just to reiterate what the strong acids are. There are only 6 acids, strong acids, there's lots of acids, but there's only 6 strong acids, and these are them. These are the ones that if you put them in solution, they will fully dissociate into their ions, a little bit like a salt does. There's lots of other acids in the world, and they only partially dissociate, and you'll treat that issue a whole lot more in Chem 112.